Okay, for this problem we have a Poisson process with rate 2 per minute. And we have various problems concerning this. First off, find the probability that at least 3 calls arrive in the first minute. So let n be the number of calls in the first minute. Well, we have a Poisson process with a rate 2 arrivals per minute, so clearly n is going to have Poisson distribution with parameter 2. So the question is, find the probability that n is greater than or equal to 3. Now, hypothetically, this can be added up directly. Find the chance of 3 arrivals plus the chance of 4 arrivals plus the chance of 5 arrivals plus the chance of 6 arrivals, and so on to infinity. That's a little bit painful, and what's a little bit easier would be to take 1 minus the probability that n is less than or equal to 2. This one is only 3 events. So sometimes it's easier to write things like this where you take the complement. This is an example where taking the complement is easier. Okay, the chance of 2 arrivals. Well, we have Poisson parameter 2, so e to the minus 2 times 2 to the 0 over 0 factorial. That's a chance of 0 arrivals. Plus e to the minus 2 times 2 to the first over 1 factorial. That's a chance of 1 arrival. Plus e to the minus 2 times 2 to the second over 2 factorial. That's a chance of exactly 2 arrivals. So the thing in brackets is a chance of less than or equal to 2 arrivals, and so 1 minus that would be the chance of 3 or more arrivals. So this works out to be 1 minus 5 times e to the minus 2, and plugging into a calculator, that's about 0.3233. So that's the answer for the first problem, that at least 3 arrivals come in the first minute. 2. So let x be the time between the third and the fourth calls. So the time that elapses between successive arrivals. So we know that this is going to have exponential distribution with parameter 2. In a Poisson process, the times between arrivals, the inter-arrival times, is exponentially distributed. And we know that the expected value of x will be equal to, the formula goes 1 over lambda, and so that's equal to 1/2. And also the standard deviation of x is the same thing, 1 over lambda, which is 1 over 1/2, and the units here are minutes. And that makes sense. If we expect 2 arrivals per minute, we expect the time between arrivals to be about a 1/2 minute, and it turns out the standard deviation is also 1/2 minute. Part 3 is the more interesting case. So x is the number of arrivals in the first 2 minutes, and y is the number of arrivals in the first 4 minutes. So we know that x is going to have Poisson distribution with parameter 4, and we also know that y will have Poisson distribution with parameter 8. Now clearly x and y are dependent. Y has to be greater than or equal to x. X is the number of calls in the first 2 minutes, and so that influences what the value of y can be. So these are dependent, so let's figure out something that's independent. So let z, let's make a new random variable, be the number of calls in the second 2 minutes. Okay, so in other words, here's 0 minutes, 2 minutes, 4 minutes. X will be the number of calls in the first 2 minutes. Z is the number of calls in the second 2 minutes. And clearly, capital Y will be the number of calls in the first 4 minutes. Then Z, this also has length 2 minutes. So that has Poisson distribution also with parameter 4. And we also observe that Y is equal to X plus Z. Okay, the question asks us to compute the probability that x is equal to k given that y is equal to 10. So by the definition of a conditional probability, that's the probability that x is equal to k and y is equal to 10 divided by the probability that y is equal to 10. Okay, now if x equals k and y equals 10, then what's left in z is going to be 10 minus k. So that's the probability that x is equal to k and z is equal to 10 minus k divided by the probability that y equals 10. Now why would I want to do this? Again, it's a Poisson process. One of our rules for a Poisson process is what happens in these 2 minutes is independent of what happens in these 2 minutes. So x and y are not independent because they overlap, but these two intervals do not overlap, and so these two events are independent, and so therefore this splits up. So the probability that x is equal to k times the probability that z is equal to 10 minus k divided by the probability that y is equal to 10. Okay, from this point forward, let's use the properties of the Poisson process. So x has Poisson parameter 4, so the chance that x equals k is e to the minus 4 times 4 to the k over k factorial. Z also has a Poisson distribution with parameter 4, so e to the minus 4 times 4 to the 10 minus k over 10 minus k factorial. And then we divide by y has Poisson distribution with parameter 8, so e to the minus 8 times 8 to the 10 over 10 factorial. That's a chance that y is equal to 10. Okay, so let's simplify this. These cancel. So rewriting things, we get 10 factorial over k factorial 10 minus k factorial. Then we have 4 to the k times 4 to the 10 minus k. Now in the bottom here, the 8 I'm going to split like this. 8 to the k times 8 to the 10 minus k. If I multiply those together, I get 8 to the 10. And the reason that I do this is so that I can split up the terms there. So this is 4/8 to the k times 4/8 to the 10 minus k. Now what are the possible values of k? So if y is equal to 10, x can be anything between 0 and 10. So the possible values of k are between 0 and 10. So if y is 10, then the most that x can be is 10, and the smallest that x can be is 0. And so we recognize this as a binomial distribution. So this is equal to 10 choose k, 1/2 to the k, 1/2 to the 10 minus k. That's a binomial distribution. So the punchline is, so the conditional distribution of x given that y is equal to 10 is binomial with parameter 10 and probability 1/2. So there's 10 events that occur between 0 and 4, and there's a 50-50 shot, 4/8, that they occur in the first minute.